It's great to be back with all of you, and again, we've got a lot of students watching online, so greetings to all of you. We're now here with a guy that I assume that the place he works is great for a lot of movie sets, because he's the laser guy, responsible for the biggest laser in the world. Ed Moses, Principal Associate Director of NIF, of the, I should know, tell me what NIF, National
Ignition
Facility. We're going to see in a few minutes.
We call it NIF.
And Photon Science, NIF, at the Lawrence Livermore National Laboratory. It's great to be with you, Ed. Ed, you've got a $3.5 billion facility, and the promise of it is that we're going to get, fusion-based energy out of it at some point, someday, some year. And I would love, in the next few minutes, we're going to give you a few minutes to basically tell the quick NIF story, and then we'll have a conversation.
Right. If that's okay, I'll just go flipping through this.
Yeah.
This is the NIF, and just if you don't mind if I stand up so I can see.
So it's a thing. It's big. NIF.
Right. So the NIF is the National Ignition Facility. It's kind of a big laser. It's really close to here. You can get here in about an hour. And if you look at it from above, it's sort of you can tell from the size of the trucks and stuff around it, sort of like the size of a football field. Our goal is to make a sun, a miniature sun on Earth. Our sun is about 1 million miles across, and we like it to be far away. It's about 100 million miles away, and we like that. We're sort of the Goldilocks planet. We're not too close. We're not too far. It's just right for life on Earth. But the problem is it only works because it's really big. It works by gravitation. So it just smashes together through the gravity of that hot hydrogen gas until it gets enough pressure and enough temperature that you get fusion burn. And fusion burn is real interesting because we're just using the nucleus of hydrogen, protons and neutrons, and Einstein's most famous equation equals mc squared to turn mass into energy. So it's a great combination. Where do you see hydrogen in water? So on Earth there's plenty of it. And the trouble is we want to make it about the diameter of your hair, right? Because if you get it down to the diameter of your hair, it's enough energy to power the Earth. This goes back to only 52 years ago, to Ted Maiman, one of the great scientists and engineers and technologists of our time. He came from Stanford, and then he went down to use aircraft, and he invented the laser. And you can see how small it was, sort of the same size as the first transistor. And they both changed totally since then. Then John Knuckles, a few days later, up at Lawrence Livermore National Lab, said, I got an idea of using lasers to make fusion happen. And he told us to do this. And he's still around talking to us. And he said, why don't you just have a gold can, could be other materials, and inside of it we have a little fuel tank of hydrogen. Remember, that's about the size of a peppercorn. And it has a little capsule wall made out of plastic. And put some lasers into it and heat it up like an oven, except you do it in a few billionths of a second and bring it up to millions of degrees. And then you have these X-rays that will be absorbed by that plastic and turn it into a rocket. And the rocket is now pushing in at very high speeds. We go in at about 1 million miles an hour, so it really moves quickly. And if you do this, you could get pressures and temperatures high enough for Einstein's equation to work. So he said to do that, and 52 years later, we're here and doing this experiments, and we're doing it on the NIF, and that's the size of that target, right? So that's full scale. So, if with that size target, you could power cities, and you could power a city like San Jose with about 400 gallons of water a year, right? That's the thought. No carbon, 400 gallons of water a year. You could power the state of California, the country, with a small swimming pool. So changes everything. That's what a real target looks like a little Klingon warship. It's about 1 centimeter high. This is how the facility works. When you go inside of it, the lasers go back and forth like lasers do. This happens very quickly because it's the speed of light. And when we finally get there, we crush that capsule together, bam. So I'm going to skip the next movie, and because I think we've talked about it enough. It's a real facility. You can go there. That's a normal-sized Livermore standing there, right? So, and each one of those things is a laser beam, And what's amazing about this is 100 times more energy than any other laser on Earth. So when you talk about technology leap, that's kind of an unusual leap. And actually, each and every single one of those laser beams is the world's most energetic laser beam. That's the target chamber. You can see those people standing under it. This is how it looks when you get ready. And that's how it looks when there's a target in it. Remember, that target is tiny, and we have to hit all the laser beams within 1/10 the diameter of your hair, which we do all the time. And we're ready to demonstrate fusion ignition now. So we're in the process of doing that. And if we did, we could think of changing the nature of our future, which is, hopefully we get to talk about it, 2 million tons of coal to power San Francisco, a pickup truck of water, per year. It's kind of different. And this is how it would work. And then I'll finish. You have to build a fusion engine where you would actually just have like a little boiler, and the targets would come in, just like this. They get hit by the laser, they put out their energy, they go out to the walls where you have a liquid metal flowing in them, they take away that energy, they go past the heat exchanger, and now something very sad happens. You boil water. You make steam, you turn a turbine generator, you make electricity. So that's the story. We start with water and we boil water, right? And it's kind of an interesting story. And you could have something that looks like this. It's called LIFE, Laser Inertial Fusion Energy or Engine. It's small, compared to a Walmart. And it would be a kind of an interesting thing. And so I'll end on that. Thank you very much.
Cool. So I guess the first question, and maybe it's a naive question, is that I sit in Washington with a lot of people talking about fracking and the natural gas revolution, renewable, solar, wind, oil is back, shale. I never hear people saying fusion.
Yeah.
And so. Is this such an exotic and remote possibility, despite the investment in the national labs, that you're not really seen as a real legitimate part of the energy options for the country and world?
I think at the moment
is that an unfair question?
No, that's not unfair. I think at the moment people have a healthy skepticism of this becoming a power source. The real issue is economics, in all energy, finally. And how economics is measured is a complicated story now as we understand the cost of carbon and the like. But people have been talking about fusion for a long time and it hasn't happened. But like a lot of technologies, at some point they're here. And what's incredible about this story to me, it's a California story, right? The laser was demonstrated in here. The idea of fusion was demonstrated in Northern California. All of the technologies that will be used in a life power plant are sort of Silicon Valley, laser diodes and the like. So this is a situation where you have a need, which is clean fuel. You have technologies. You have a system that mitigates the complications of the technologies you have. And the question is, can you show the performance on the NIF that you prove that it can be done? And we're sort of on the verge of doing that. So I think there's skepticism, but I think that could change sort of, as I say, in a few picoseconds or a few trillionths of a second when we get burned.
Years ago in the early 1980s, I mentioned to you in the green room that I had been up at Livermore last time I was there. I was actually in a car with a guy named Herb York, who's a well-known scientist and national security expert. And the other guy who happened to be in the car was Dan Ellsberg. When we went past it, there was a sign there that said, do not discuss classified information beyond this point. And Ellsberg goes, let me think of something classified to tell you. But when we went in and I saw and had a tour of Livermore, I saw this this had to be before this facility, which was, I guess, built in 2009. But there was this other kind of football size. There was a giant thing that looked like out of the movies that was the other, fusion effort. And we were talking earlier in the conference today about failure and embracing failure, that failure isn't always a bad thing. You learn things. So were you part of that? Do you remember that facility that I think I saw?
Yeah, I remember it very well. I actually wasn't working on it. The idea of this happened in 1960. There really weren't any lasers to play with effectively until the early 70s. Since that time, Livermore has had the lead on these scale lasers, and we went from our first laser, Janus, to Argus, to Shiva. The one you're talking about is Nova. And they sort of went up a factor of 10 each one. And it's sort of like releases of semiconductor technology. So I don't think any of them were thought to be failures. They were all thought to be actually phenomenal successes.
Was Nova a success?
Yeah, Nova was a tremendous success. In fact, from the point of view, it showed exactly the scale that we needed and still think we need to do ignition or propagating burn using fusion. And that's how the NIF was finally decided to be built, based on the results of Nova. So I don't think of these as failures at all. I think of them as a part of an evolving story of knowledge creation and understanding where we are.
Now, what do you think the technical barriers are at the moment? When you said you were right on the verge of a result that could be a game changer, I could hear whoever is president. We've got that choice next week, I guess. But is it next week? Okay, I've lost track. Thank God it's next week. But the president calling and saying, Ed, good job. You've changed it. So what is the technical barrier that you see right now to achieving a definitive, undisputed success?
Okay, so right now we're in a situation where we have taken this peppercorn, shell that I showed you and compressed it, actually smaller than the diameter of a hair. And we've started to see burn, but we haven't seen propagating burn, which is kind of a first of its kind. So the question is, why hasn't it lit off, as we say? And, we don't think it's a technology issue. We don't think we need a new laser or a bigger laser. We think right now is looking at our diagnostics as we compress this hydrogen, from 2 millimeters or peppercorn size to hair size. It sort of has a little bit of a catcher's look, a catcher's mitt look, it's sort of wrapped around the hot spot in the middle. So what's happening is the pressure starts going up, and I don't mean to low pressures. It doesn't go up to millions of atmospheres or hundreds of millions or billions. We're now at 150 billion atmospheres, which is like it is in the center of the sun. But we got to have another factor of 2. So we're now doing our final, hopefully, tuning experiments to understand how to make that round. So we think we have the system we need, and we're just working through the physics.
I don't know if any of you picked up, or hopefully all of you picked up, not only our Underwriter Boeing stuff, but the Atlantic magazine article, which is out. And one of the features in this magazine this time is what we call our Brave Thinkers series. And I finally read this yesterday. And there's a young man in here named Taylor Wilson, and it says nuclear scientist. He says when he was 14, Wilson, where's our young man over here? When he was 14, this is something to think about, Wilson built a nuclear fusion reactor, then a bomb-sniffing device that impressed even the president. Now 18, the prodigy is skipping college and using a $100,000 field fellowship to try to crack the riddle of harnessing energy from nuclear fusion, a feat that plenty consider impossible. So if you know this guy.
Yeah, I know Taylor.
So tell us when you met him,
I met him about 3 months ago. I actually wrote him a letter when I read something like that, and I said, Taylor, why don't you come by and see how
the big guys do it.
How the big guys play, because we always try to recruit talent, and my view of it is, someday he'll work at the lab, and so
Maybe
he came.
He's the next Elon Musk.
Yeah, well, he came by, and he is one of the word is profoundly gifted, and he clearly.
Show what he did.
Hi, my name is Taylor Wilson. I'm profoundly gifted. I said, my name is Ed, and I'm working hard. But anyway,
works in Hollywood,
right?
Yeah.
But he actually is a remarkable young man, and he didn't build a fusion reactor. The press sort of took it to a limit but he did show fusion, and you can do fusion at low scale, and he has very clever ideas. And we spent a day with him. And then I was just at the International Atomic Energy Agency meeting on fusion energy last week, and I saw him again down in San Diego. I think he's a brilliant guy, and hopefully he'll be very successful.
So one sort of silly question and one serious, and I'd like to open up to the floor. But in a way it's serious. When I read about Taylor, he made the interesting point, which has come up frequently today, that he says young people don't know what to be afraid of, that they're more provocative thinkers because they haven't been regimented, essentially, to take that. And so he was sort of critiquing the larger science industry that's full of regimented minds and regimented people. And maybe that's it. But as we're discussing innovation, we're discussing science. Do you think that the system needs to be refreshed? Do you think you need to have an out of left field hit every once in a while to make those breakthroughs?
Yeah.
Given how profound the science is. Is that true in your work?
I think that's totally true, and that's why we recruit. That's why I wrote Taylor. I mean, I don't know if I'll have an idea today or tomorrow or a week or a month, a year, but he will have ideas, and you have to have an infrastructure around these guys to take advantage of them. And if you don't, a lot of these things just die on the vine. But it's our goal to look for people, young people, and great ideas, and nurture them. So I do think you need these ideas. I always go back to Ted Maiman. He went up against Bell Labs, MIT, the whole crowd, and built a laser that they had decided would not work. And he built it with Edmunds Scientific, a Bell and Howell lamp, and stuff like that. It's kind of an interesting story. And that's because he was a good physicist, a good engineer, a good inventor, and he wasn't afraid of what other people were saying. And, they never really recovered from it, But he was, he just pushed that envelope to the limit. I think that's what we all need to do.
Does China have anything like this going on?
Yeah, as a matter of fact, we're in an interesting place. The NIF, which would never work, now works. It meets all of its specifications as a technology element, and because of that, the Chinese are building a NIF. They have a much better name than ours. It's called Divine Light, right?
They call theirs Divine Light?
Yes, they do. And
I hope somebody's tweeting that.
The French are building laser megajoule. They say it backwards, but it's actually almost built. They're just putting the laser stuff in. I think it'll be operational. The Russians are building an IF also. So we plowed.
Are you competing or collaborating?
Well, I always tell the joke we collaborated with the French, so they aren't following us exactly. We don't communicate with the Chinese, so they are following us exactly. And the Russians are sort of in between. We also work with the Brits and Japanese, and also Korea is now getting very interested in this. This has sort of been flying under the radar screen for a long time. But as NIF has come up and our results have become better known, there's a lot of interest, and there's a lot of investment across the world.
And is there a first mover, first success advantage in this game?
Well, when I was in China and I was meeting, this was about a year and a half ago or so, and I met, maybe 2 years, I was met with the Chinese Academy of Sciences, the deputy chair. That's a big deal, and they said, well, in that very Chinese way, sometimes it's good to be second, because we have to learn. On the other hand, I like the Andy Grove's view of it, is when you're ahead, run as fast as you can, right? And I think there's, as people here know, the know-how and art that you develop in putting these systems together over many years is sort of more important than the publications and our infrastructure of vendors and the like. I think we have a good running start.
Before I open to the public, the one area, the policy area I want to ask you is that, I always grew up, when I worked for Jeff Bingaman in the Senate, you're sort of inculcated with these notions on how important the national security labs are across the country, being a backbone, partnered with universities, often partnered with the private sector, in which there are cooperative research and development agreements, universities, and so that there's this ecosystem in which there are a lot of players that move in and out, share ideas, but what drives a lot of that is money and resources. And I am, personally worried that when I look at the debates about budgets in the future, and I think part of the reason why this conference is important, or at least trying to put on the table, is that dollars in certain areas matter more than dollars in others. That you get a multiplier out of innovation, out of science, out of the impacts that come, and that there are both commercial, but there are also life sculpting and socially sculpting benefits that come from them. how is, I mean, you're at Livermore, so maybe this is an inappropriate question, I'm not sure, but are you funded at levels and do you see yourself being funded at levels to help you achieve, this very important step in energy options?
Oh, okay.
Does funding matter?
Let me answer it a couple ways. First of all, the ecosystem is totally a good representation of the situation. So we have 3,000 vendor partners who helped us on NIF, and from mom and pop machine shops to large aerospace corporations. We work with about 150 universities around the world, and that's where we get not only talent, but those young kids like Taylor who show up. And, we work with government labs also and internationally, as I just said. But it goes forward on money, right? If you don't have resources, you can't have this ecosystem. And it's sort of like, watering the garden. And, everyone's always concerned, especially now that, you won't get enough water and fertilizer to keep this happening. And if you don't, it will go somewhere else, because these ideas are, big enough and important enough, whether you're talking about strategic security or energy and water or basic science and competitiveness. This is what happens. I recently gave a talk, actually, at Dartmouth about, from Newton. How did you get from Newton to Maxwell, to Planck, to Einstein, just to Bethe, to Goddard, to Knuckles, to make this story happen? And you're sort of looking at a 300-year story, and in every case, there was important people at important times who not only were thinking, but were supporting those thinkers. They showed up, to make sure those activities went along, and we're only here because of them, and that's how I think about it.
Great. Well, thank you. Let me open to the floor. Do we have questions? Yes, right over here on this side, and we'll move to this side of the room. But in this corner?
How much energy does it take to power one of the lasers and the entire plant?
Can you speak a little more loudly?
Sorry, how much energy does it take to power the laser or the entire plant?
Well, this is always the question I ask people on tours. And by the way, you're all invited to tour the NIF. It really looks much better in 3D than that. But and just let us know, and we can, you can call Brianna Bishop, who's here. She'll arrange it for you. This is always the question I ask people, and the answer is remarkably little. It takes about $5 in electricity per shot. And if you think about it, if it took a lot...
Can you buy your own shot when you visit?
Yeah, we could have a little brick. We haven't thought about that, put your name on it. But yeah. You can. But if you think about it, if it costs a lot in electricity, then you never could make a power plant, because you're doing 10 times a second or 600 times a minute. So, and then our goal is to get it down to around 50 cents in electricity per shot.
Wow. Yes, right over here. This gentleman. We'll hit a lot of folks here.
Hi, Jim Hollenhorst, Agilent Technologies. So let's say NIF is completely successful in reaching the goals that you've set for it. What are the challenges to turning it into a power plant, and what's the time scale for making that happen?
Okay, so NIF is a research and development facility, so it only shoots about once every 10,000 seconds, once every 3 hours is what it normally does. And over long periods of time, we shoot it once a day, but it's a data machine. It's not a power machine. The question is, how do you get it up to 10 times a second? So that's the question. If you did 10 times a second, you could make about 2,000 megawatts of thermal energy, because that's all it is. It's a heat engine. And that would be about 1,000 megawatts of electrical energy. And at that point, you're sort of a power plant. So the question is, what do you have to do to get it to 10 hertz? Well, if you remember that picture I show of Mayman's laser, it had that flash lamp, which is sort of 19th century technology. It's not quite Matthew Brady, but it's, and that is a very inefficient device. And not only is it inefficient electrically, but it doesn't couple energy into the laser well. So we've invented laser diodes in the mid-90s that are quantum mechanical devices that just couple nicely. They're extremely efficient. And, maybe some of people here, guys and gals here, have, commercialized that. And so the goal is to just put that together. We have done that at small scale. It looks like it works, and it gets the efficiency up about a factor of 20. And that turns it into a place where it's easy to cool and make it happen. Most of the plant is, that you look at is the kind of things you buy from GE or Siemens or the like. It's, turning thermal energy into electrical energy. So that's one of the big issues.
Yes, right here in the front.
Lynn Joltz, Telemuse Partners. As a Berkeley physics alumna, I did tour Shiva Nova as a student. I even remember the yin-yang magnet. And it was a very exciting time, but the budget was cut. And a lot of the people who devoted their life to plasma physics study ended up going elsewhere to try to survive. It was a real difficult time for researchers at that time. I was fortunate. I was able to go off into the computer industry. Berkeley entrepreneurship, operating systems, the whole thing, and had a great career there. You're now doing really exciting work again. But the budget is threatened again. And it takes 8 to 10 years for a person starting off at university to get that real gravitas to be able to do the true research. How are we going to ensure real continuity in research for our younger generations?
And you're totally responsible.
Well, the president writes me every day about how you're doing supporting the research. But anyway, I think this is a really important question. And I really say it very seriously because we have 10 sets of experiments on the NIF right now that are 3 years to 4 years long that support fundamental science. And the question you have as a facility director, when you commit to those faculty members and those students, will that facility, will the laser time be there, shot time be there when they get there? Because that's a big responsibility. The way we do that right now is we work really hard to make sure that the quality of the experiments that are accepted on the machine, and this is through peer review and the like, are the very best, right? And because of that, they sort of get a momentum of their own. And we also have off tracks, for them if things aren't going as well as because it's research, if they like. So we sort of try to protect them. But that is a very important question that we deal with.
One of the interesting questions, I'll go to this gentleman here, and there's another question on this side, and we'll take these two, and then we'll so right up here. But I think one of the questions, again, when you think about funding, particularly this is an area where we've kind of gone back and forth today between commercial and national security or sort of national agenda items. And I think that from I'm not just lamenting the past, but when I think about people like Jeff Bingaman, Bill Frist, a number of other people who are so committed to science and technology, that number is diminishing, and it's not just the technical sophistication of members of Congress, because that's probably always weak, but the level of curiosity in these kinds of questions is diminishing. Their staff level is there, but I do think that at some level there is something developing that I fear is unhealthy for the country, which is a lack of curiosity, a lack of understanding about a kind of commitment to deep research, and I'm wondering if you feel that in any sense.
It's sort of an interesting question. I don't know how many of you have Zoe Lofgren as your congresswoman.
She's great.
Yeah, but she's totally committed to NIF. I mean, she calls me, she asks me how we're doing. She arranged for 100 congressmen and congresswomen to write a letter in support of NIF recently, and that's a hard letter to get. And Senator Harry Reid has been very supportive, and he was recently on the radio and supported us. On the other hand,
any Republicans?
Yeah, the Republicans. On Zoe's letter it was about 60-40 Democrat-Republican, so that was very, very helpful. The other thing is because NIF has strategic security and energy security and basic science. You would think that was good to have all those constituencies, but it complicates the politics of it. Like whose shot is this? Is it mine or is it someone else's? But if you're in big programs, and I say this to students especially if you're listening, so it's sort of the cost of doing business. You have to think about who your constituents are, just like in business.
I think you should call it the Bush-Clinton laser show, since we'll probably have Bushes and Clintons running for a long time from now. Let's go to this gentleman, and this gentleman will go and take both these questions.
I was also wondering, since you're showing how in nanoseconds that the ball you were talking about got lasered. You said there was something like a rocket?
Yeah, so what happens is that your question?
No.
Yeah.
Well, I was wondering if since it was sort of like a rocket, would they ever use that for rockets or like other modes of transportation? If they did, how big would it have to be?
There's a lot of talk about rockets today.
This is such a better question than I was going to answer. So the question about using lasers for rockets has been debated forever. Now the way you do it might be a little bit different than you think. Just like this, if you shined a laser at a material and got it hot enough that it would start ablating, or material would start flying off of it because it was hot, then it would push what you were doing forward. So it's an idea that people talk about for deep space travel, right? So yes, people have thought about it. I have someone who works for me. I wish he would stop thinking about it.
Great. Final question. Yes, sir.
Hi, Charles Che. Thanks for being there. A question about a comment you made about a milestone for propagation. Could you describe that further? And is that related to the frequency of ignition that you had answered a little bit earlier as well?
I'm not sure exactly what you're asking, but I'll try to restate it, and then if I have, let me know. So when you talk about a normal fire, a chemical fire, when you have a propagating burn, that means the act of it burning heats up the fuel and sucks in oxygen and then makes more material burn, and then it propagates out. So if you had a pile of wet leaves and tried to burn it, it might get smoky, but it wouldn't propagate. Dry leaves, you could have that happen. It would just start burning. So our issue is putting this fuel together, this hydrogen fuel, at high enough pressures and high enough temperatures that when it starts having the fusion reaction continues to heat the fuel, which increases the rate of the fusion burn so that it propagates out. So where we are right now is we've started the spark, but we haven't held it together long enough, which, by the way, is a few trillionths of a second, to make it propagate out. So that's where we are. Is that answering your question? Okay.
You're the best guy from any national lab I've met with hand gestures. Have you ever done Jon Stewart's show?
Well, that's because I grew up in New York in an Italian neighborhood.
Have you done Jon Stewart's show?
No, I have not.
You should. You'd be great.
Okay. Well, you arrange it and I'll go there.
Anyway, I want to thank you all very, very much. Thank Ed Moses for joining us here. This has been fascinating. Round of applause. Thank you.
Thank you very much for having me.
And I look forward to going out and see the facility, and I'll pay my $5 for the shot from the 100.
Okay, and really, if you want to see it, Brianna can arrange it for you.
That's great.
Okay.
Rihanna's here. Great.
Right.